Hello everyone and welcome back. Now that we have completed our look at value noise with both theory, 2D and 3D, we're now going to move on to Perlin noise, starting with some Perlin 2D noise theory. Lee?
Right. Now that we've got the value knocked out, we started off with one of the simpler noises that we could deal with. Just random noise or random numbers being converted to noise being the simplest. Value noise adding to that, making it a little bit more complicated. We're going to go yet another step and we're going to be implementing Perlin noise in 2D. We'll also come back after that and do it in 3D. Now, the Perlin noise that we're going to be implementing, or the flavor we're going to be using, is called the improved Perlin noise. There is actually the original Perlin noise, which is the noise that was used in the early 80s. And then Ken Perlin went back and wrote another paper on it and revised his original noise to make it better, hence the improved noise. And then after that, he even came back again and made a new noise called simplex noise, which is improved over the improved Perlin noise. And we'll get to that in a later set of videos after we deal with Perlin noise. Now, there's a couple of references that you can do some initial reading on if you're interested in. The very first site is basically if you do a search for Ken Perlin, Perlin noise, and I threw in Academy Award because I knew he won an Academy Award for it. Now, a lot of people think that he won the Academy Award for Tron, but he got a technical award for basically noise, all the work he did on noise throughout the 80s, not specifically just Tron, but his work in general. Now, the nice thing about this site is it gives you a little background, but at the bottom, it has his initial or his original implementation of Perlin. Now, this is the original implementation and not the improved, which is what we're going to be working with. But if you want to see what the original Perlin noise looked like, you can check out this site and look through his code. Now, later on in, I believe, the late 80s, about 80, what was it? Hold on, 98. So as detailed in 1998, roughly circa then, he wrote another paper describing some improvements that he made to make the original Perlin noise better, and that's what this paper discusses. It doesn't give any code, though. It just it gives some of the calculations and the theory behind what he was thinking for his new noise. Now, another site that you can go and look at is his GDC talk that he did back in 1999, which is called Making Noise, and the link is here. So if you want to look for this presentation, it's just basically a slideshow that he gave that goes through the history of noise and his progression through the different versions of noise, which again has some interesting reading, but doesn't really get in depth on the theory behind Perlin noise and how it works. For that, I found this paper, which is called Simplex Noise Demystified. Now, the nice thing about this paper is not only does it have a very detailed discussion on simplex noise, at the very beginning of it, he goes into a really well thought out discussion on what Perlin noise is and how it's created. And this is where I went and got probably the best idea of what was going on behind Perlin noise and how it's implemented. And he discusses how Perlin noise works in 2D as well as 3D. But one of the nice things about this one is at the end of the paper, there is an implementation of both the classic 3D Perlin noise as well as simplex in 2D and 3D. And the code that we're going to be doing today is very heavily influenced by this code here. This is written in Java, so I've ported it over to C#. So, but aside from that, and a couple of tweaks here and there, this forms the groundwork of all of the noise that we're going to be doing for Perlin 2D, which is not here. This only has Perlin 3D, but I use this as the basis to reverse engineer Perlin 2D. The Perlin 3D as described here, and in the later videos when we get to Simplex, the code for Simplex 2D and Simplex 3D were also influenced by the code that was in this site. But in total, these 4 sites were the major references that I used for learning about Perlin and Simplex. So let's get into what Perlin is. So if I go over into Photoshop, you may remember this diagram when we were discussing value noise about having a unit square where we sample at each of the corners and get a value of noise, and then we interpolate to the noise that would be at the point that we're actually sampling. We're going to be using the same premise here, but Perlin noise isn't a value noise, it's a gradient noise. So what happens is we take a gradient like this, just a black to white gradient, and we apply it in such a way that we take the average of the values at the point where the gradients overlap and we return that as opposed to using random numbers. Now the way that is done is we need to calculate 2 different angles. The very first angle that we're going, or vector that we're going to figure out, and I'll use green for this, is going to be, let's see, do I have a grid on this one? It doesn't look like it. Oh well, I'll try to fudge it. So what we're going to do is we basically draw lines. Oops, I see what I'm doing. I don't want a shape, I actually want this. All right, let's try that. So we're going to just draw a vector from each of the corners to our point. So we're calculating from each point a magnitude of vector to our point. Now, what we're going to do as well is we're going to randomly pick any direction from our vector. For now, we're going to revise this. So what we do is we could randomly choose a direction that the gradient is going to face. Let's say for that case, we're over here. This way, we're pointing this way. And we're pointing so that way. And we're pointing this way for each one of these corners. Now, the way the gradient works is we can take a gradient. I'm just going to duplicate it. Move it up here. Turn it on. Change its opacity to be, let's start with 50% so we can see what's happening. And I'm going to start in the lower left-hand corner. So if I take my gradient here, and I put its center in the corner, and I rotate it so it's kind of aligned in the direction of our vector, which is this blue arrow here. And this is not, for visual appearances, I'm going to scale it up so it covers our entire unit square. So normally the gradient in our noise will be calculated procedurally, so it'll automatically scale based off of the distance. We won't be doing that by hand like we are here. So this would give us our first gradient. Now take this one again, bring it back up, and now I'm done with this one. I'm going to have 4 different ones, so I'm going to multiply it by 25. But I want to have this one a little bit darker so I can see which one I'm working with. So let's go ahead and do the lower right-hand corner. So I can position this here, rotate so we're roughly in the direction of the vector. Oops. Scale up. Back to 25. Go ahead and change this to 50 so I don't have to constantly do that. Duplicate this one, turn it back up, turn it on. All right. Let's take this one, move it here, rotate so we're pointing in the direction, because I want white to be in the direction of the vector and black in the opposite. And then, oops, I'm trying to work across the lag, so scaling's a little bit awkward. All right, so we take that one, duplicate this one last time, move it up to the top, and let's set this one down to 25. Now the opacities and the actual shading values are not going to be exactly what we'd get with the real noise. This is just more for demonstration. Right. It's close enough. So if I take those, wondering if it will set each one of these to multiply. Nah, it's just going to gray it all out. No, we'll leave them the normal. Oops. The mouse, come on, there we go. So what we're doing is we're taking each one of the gradients and they're going to have an additive effect, and then we'll average out the color at this point. And that gives us our color contribution. Now, where I said that these are chosen at random, they are chosen at random, but they're chosen from a random selection of preset values, those being vectors that have been pre-chosen. And in Perlin's improved implementation, there are 12 directions that he's defined. Now, the way those were chosen were based off of, if I go back over here, because it's a lot easier to point it out than it is to replicate this little diagram, is if you were to take a unit cube, basically a cube that is one unit in every direction, and then from the center of it, draw a vector to the center point or the midpoint along each one of the edges. So where a square has 12 edges, if you were to draw a vector from the center to the midpoint of each one of those edges, that represents 12 different vectors. So if you take those 12 different vectors and randomly choose which one of these vectors to use, and then you apply that to each one of these corners. So at this corner, our direction or vector could be one of 12 different ones. Same with each other one. And then what we do is we take the dot product between our vector that goes from that corner to its center point from the random vector that gets assigned, and we use that as a multiplier to our gradient to calculate the value at this point. Because if we do a dot product, you get a number that's going to be between 1 and -1, depending on the angle between two other vectors. So we use that to calculate everything out. And that is how we get Perlin noise. So it's a bit it's a bit convoluted in the way it works. You just have to take your time, read through it, play with it. Now, when I did the Photoshop thing, that started helping me understand how the gradients and the vectors were related as opposed to just reading through pure equations. So, but in the next video, we'll actually start implementing this. And then once we see it, once you see the code and how it's implemented, and then we put it into our little test bed, it should come full circle, and you should be able to have that little light bulb go off and go, oh, that's what it's doing. So hopefully as we move along, it'll become more clear. So.
Okay, so with that, that will wrap up this video. Thanks a lot.